So for number one, taper per foot requires that you know the formula for taper per foot. Anybody remember what it is? Taper is equal to big D minus little d over length over 12. So in this problem, what do you think big D is? 2.75 minus, what do you think little d is? 1.125 over L, 9 divided by 12. So we keep doing some work here. 2.75 divided by 1.125 is 1. Subtract, yeah. Subtract. 2.75 minus 1.125 is 1.625. 9 divided by 12 is 0.75. And if we divide those out, yeah, 2.16, 2 1/6 inches. But normally taper per foot usually goes to 5 decimal places. We're just going to go 2.16 for feeding. That is inches in diameter per foot of length. Taper per foot is always inches per foot. What that's saying is the diameter here changes by that much per foot. Now the next one down here actually looks a lot more difficult than it really is. We want to solve for XL, but I give you the numbers for everything else. Z is 170. R is 150, so it's being 150 squared. XL is what we're solving for. XC is 210, and we're going to square that, of course. So now, I have to do whatever I can inside that square root. That's an enclosing symbol. What I can do there is square the 150, which would be 22,500. Now I'm going to start to solve this. To get rid of that square root symbol, I am going to square it. Now this square root symbol square roots this whole side of the equation. That's important. If it was just on a part of that side of the equation, this doesn't work. But since it's square rooting the whole side of the equation, I can square it. 170 squared is 28,900. Here the square root and the squared cancel out. That's 22,500 plus the XL minus 210 squared. And then this square does not cancel out. No, that's still there. See, that's not on the whole thing. That's just on this piece, and there's more stuff underneath there. Now I'm going to subtract the 22,500, which gives me 6,900 over here, equals what's left over here, XL minus 210 squared. Now we've got to go the other direction. This whole side over here is squared, so we need to, yeah, it would be 6,400. You're going to be picky and making the right answers. I see how you are. So since that whole side is squared, we have to square root it. We got to square root this. The square root of 6,400 is 80. That works out a little bit better anyway. Over here, the square root and the squared cancel out. We've got XL minus 210. And then add 210. We get 290 equals XL. How many of you had that? How many of you want to see another one similar to that? Now this XC is a variable in itself. This C here has nothing to do with this C here, just so you know. for C when F equals 60 and XC equals, what do I want to do here? We'll just say XC equals 1200. Let's see what you can do there. I'll give you a minute or two. So for XC, we put in 1200 equals 1 over 2 times, I'm going to put in 3.14 here, times 60 times C, and we are looking for C. So I'm going to combine all this crap first. I probably shouldn't call it crap. All this good stuff first. 376.8, you got it. So 1200 equals 1 over 376.8 C. Now, how on earth do I solve this? My variable's on the bottom of a fraction. We don't like having our variable on the bottom of a fraction. Now it's in a proportion. We can solve it. Remember the cross products of a proportion. In proportions, we have one fraction equals another fraction. There's nothing else there. Cross products have to be equal. So 1 times 1 equals 1. Going this way, 1200 times 376.8 C 452,160. Does that look right? C. Those two things have to be equal. So 452,160 C equals 1. Now what? Divide by 452,160. So C is, now that 2.211, notice there's a E negative 6 on the end there. That's scientific notation. So that's what that's saying. Well, it's saying the decimal point has to go 6 spots left. So it's really only 5 zeros, but it's 6 decimal places. So technically that is 2.116 micro. C is in farads, the units. You don't need to know that right now. That's capacitance, yeah. Okay. Well, it didn't. So it gave you the 0.0000. Perfect. Round off error somewhere. Just want to do one more? Okay. Let's do this one. Solve it for XC when R is 50, XL is 90, and Z is 130. Let's see what you come up with there. Go for it. Okay. So I've got the numbers put in there. First thing, oops, this should be squared here, 50 squared. So I'm going to go ahead and square that 50. Got 2,500 there. Now there's really nothing else I can really perform with the numbers, so now it's time to start to solve. So, yep, that square root applies to the whole side, so I'm going to square it to get rid of it. So I square this, which is what, 69 What does that come out to be? That's right. I'm missing the one. I knew it looked. So we've got over here 2,500 plus 90 minus xc squared. And then we'll subtract the 2,500. So this is 14,400 over here equals 90 minus xc still squared. Now that square root, that squared applies to everything on the right side, so we can cancel it by square rooting it. So this is 120 here. Square root there cancels out the squared, so I've just got 90 minus xc. We need to treat this as a negative 1 xc. So now we will subtract 90. We've got 30 equals negative 1 xc. And then divided by negative 1, negative 30 equals xc. If you finished your quiz, I want you to look at the problems I have up here for you. A couple of graphing problems. And I do have them set up in pairs for a reason. So graph 1 and 2 on the top graph and 3 and 4 on the bottom graph. And we'll talk about them in just a little bit. Okay, so the first one here. Where do we start graphing that? Positive 1 right there. And then what do we do? Up 1 over 2. You know what? I screwed up there. To make that work, it had to be negative 1. So we're going to do that. We're going to adjust that just to fit my devious goals. We're making negative ones. We start at negative 1. It doesn't matter that you guys graph a little off. We'll be able to see on mine. Then we go up 1 over 2. Up 1 over 2 more. There's that line. Second one, where's that start? Up 6. From there, what are we going to do? Down 3 over 4. You know what? I'm an idiot. That one would have worked. I'm not as dumb as I think I am some days. Yeah, but there's a reason why I wanted it there. So anyway, the next set down here, 2x minus 3y equals 6. To graph that, we have to solve for y. So what are we going to do to solve that for y? We'll subtract the 2x. We've got negative 3y equals 6 minus 2x. And then we divide by the negative 3. So that negative 3 is gone. Y equals 6 divided by negative 3 is negative 2. And negative 2x divided by negative 3, positive 2/3 x. So we start at negative 2 here, and we go up 2 over 3. Up 2 over 3 more. The next one we have to do the same thing with. We've got to solve that for y. What are we going to do? We will subtract x from both sides. 2y equals 10 minus x. And then divide by 2. So y equals 10 divided by 2 is 5. Negative 1 divided by 2? Negative 1/2 x. 1 over 2x. So that starts at 5, right? And from there it goes down 1 over 2. So we've been graphing these single equations for a week or so now. We should be getting good at them. Now these equations are picked for a specific purpose. What we're going to start talking about today is a system of equations. If I look at each of these lines, what does that line represent? What does this line right here represent? It represents, from this equation, all the possible solutions to that equation. If I pick any point, if I pick this point right here, I trace it down, that's x equals 1/2. Trace it this way, that's y equals 1 1/4. That's every point on that. If I find this x coordinate and y coordinate, it is a solution to this equation. So then the green line there is every possible solution to that equation. When I'm looking at a system of equations, I want to find numbers that are solutions to both equations at the same time. So if I'm looking at a system of equations, what I'm saying is, given both of these equations, are there any sets of numbers out there that are solutions to both of them? Yeah, where is that? It's on the graph where the two lines cross. That point is on both lines, which means it's a solution to both equations. That coordinate, 1, 2, 3, 4, 1, 2, 3, is the coordinate 4, 3. If I test that, if I put 4 in here, 1/2 times 4 is 2, plus 1 is 3. That works. I can do the same here. Negative 3/4 times 4 is negative 3, plus 6 is 3. So the second one down here, these points cross over here. 1, 2, 3, 4, 5, 6. 1, 2, is that up 2 or 3? That looks like it's up 2. So that's at 6, 2. I can test each of those. 2 times 6 is 12. 3 times 6 is 6. 12 minus 6 is 6. This is 6. 2 times 2 is 4. 6 plus 4 is 10. So it is a solution to both equations. So what we're going to start out with, the simplest way to solve these systems of equations is just this, graphing them. So if I have an equation like y equals negative 2/3 x plus 1, and I have another one like, let's see what I put in here. 3x plus y equals 15. Graph those quick and tell me if you see if we can find the solution. So as we graph the first one here, where do we start? Positive 1, okay, there's our first point. And from there, down to over 3. The second one requires us to do a little bit of work. What do we have to do? Just subtract 3x, right? So y equals 15 minus 3x. So that's going to start out at 15, right? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Which, was it going through there? And there. We get that line right there. That coordinate, by the way, is 6, -3. A little tough to graph when that y-intercept's so high. You'd have to really have a lot of space at the top of your graph. I don't know if you're seeing it yet, but I'm sure it's not much of a stretch to realize graphing is maybe not the easiest way to solve these, but it's the first way. This one, even though it does come out to be integers, is tough to find. These other ones weren't so bad because they were, lines that stayed right on the main part of the graph. But if I had one where the solution was a fraction or a decimal, it'd be almost impossible to find that solution on the graph. So for right now, we're going to do some very simple ones graphing. And what I want you to do is in your big book, turn to page 409. Exercise 17-1. And I want you to do some of those problems, solving these systems by graphing. I just have you work on that for about 10 or 15 minutes. Then we'll take a look at, okay, how could we work on these in a bit more of an exact way? Okay, let's see how you're doing. Are any of those getting you really stumped right now? More than usual? Well, let's take a look at an example here quick. So here, for number 1, y equals -1/2 x plus 3. Where would I start? Positive 3, and then from there, down 1 over 2, down 1 over 2. I keep going. For the second one here, start at -2, up 3 over 4, and right there it seems to be, that point would be 4, 1. Even if you had grid paper to graph on, it's still tricky finding that where they cross. So, yeah. But what we notice here is where those cross, this value of y and this value of y are the same, aren't they? And this value of x and this value of x are the same. Well, because this y and this y are equal, we can also say that this must be equal to that. So I can just do -1/2 x plus 3 has to equal 3/4 x minus 2. Now I only have one variable, and I can solve it for that variable. I'm going to get rid of, I have an x on each side, right? So I'm going to get rid of 1. I will add 1/2 x. So 3 equals 3/4 plus 1/2 is 1 1/4 x minus 2. And then plus 2. So 5 equals 1 1/4 x. And then divided by 1 1/4. Because it's 4 equals x. Now that's just x. We need both x and y. We have to have that coordinate, right? X and y. We got to find y yet. So I'm going to go back. We know that x equals 4. I can go back to either one of these original equations and put in 4 for x. -1/4 times 4 is negative 1. Sorry, that should be negative 1/2 times 4. That's why it didn't look right. Negative 1/2 times 4 is negative 2. Negative 2 plus 3 is 1. So y equals 1. So we got x is 4, y is 1. There's our coordinate, 4, 1. Does that make sense? Now this one was simpler because both equations were in that form of y equals. So I could just set the two things equal to each other. A lot of times we are going to have to manipulate the equation or rearrange the equation so that we can do stuff, something like that. For example, we might have y equals 2x minus 3. And then we might have 3x minus 2y equals 4. Right now, I can't just put one equal to the other, can I? I do have that this one equals y. I could solve this one to make this one equal y, couldn't I? But I don't have to go through that much effort. I know that this y equals that y. I could replace that y with the other y. That wouldn't do any good, just be putting in a y for a y, wouldn't it? But since this equals that y, I can put it in there. Let me show you what I mean. Instead of 3x minus 2y, it's 3x minus 2 times, well, y equals 2x minus 3 equals 4. Now again, I'm down to a single variable, so I can solve. Remember, our steps are always, when solving an equation, combine everything that you can on each side. So here we've got the left side here. Nothing to do with the 3x, but we've got negative 2 times the parentheses. Negative 2 times 2x. Negative 4x. And negative 2 times negative 3. Positive 6. And we're going to stay on this side. Anything else we can combine? 3x and negative 4x make negative 1x. Nothing more we can combine there, right? Anything we can do on the right side? No. Now the second step is always check to make sure, is there a variable on both sides? No, the variable is just on one side, so we're good there. So now we can start to solve this. To get x by itself, we're going to subtract 6. Negative 1x equals negative 2, and then divide by negative 1. X equals 2. Now that's important, but we still need y. So I'm going to come up here, I can either replace this x with 2 or this x with 2. Either one would give me y. But which one looks like it's going to be easier to use? Yeah, since that's y equals already, all I have to do is put in the number. Perfect. 2x becomes 2 times 2. 2 times 2 is 4. Minus 3 gives us y equals 1. So that solution becomes 2, 1. Now here, none of these are in y equals. Now if we had x equals, we could do that as well. But none of them are in x equals form either. So we're going to have to make one of them into that form. You can make either one of them into that form, but if you want to make this as easy as possible on yourself, you have to learn to find one that's easy to do. Okay, if we look at this top one, the coefficient on the y, the number multiplying the y is 1, right? That's going to be easy. If you divide by 1, you don't get any ugly decimals or fractions. If I tried to solve this for x, I'd get halves. Actually, that wouldn't be so bad. Solving this for x, I would get halves. Solving this for y, I'd get thirds. That can be really ugly. You know, dividing by 2, the very worst, you can make it a 0.5 and work with decimals. Dividing by 3's never come out nicely. You have to work with fractions. But this top one, since this is a 1y or just a y, I'm going to solve that one for y. To solve it for y, all I have to do is get rid of the negative 2x. It's negative 2x, so I get rid of it by adding 2x. So I'm left with just y there. 12 plus 2x can't be combined, so that's just 12 plus 2x. So that replaces my top equation. So now this y is equal to that y. So this goes in for that. Notice I had to put it into the other equation. So I've got 2x minus 3 instead of 3y. It's 3 times 12 plus 2x. And now it's time to solve. So I see those parentheses. Does that work left to right? There's nothing to do with the 2x. Multiply by the negative 3. Negative 3 times 12. Negative 36. Negative 3 times 2x. Negative 6x, and that equals negative 4. And then, got to combine still. 2x and negative 6x make negative 4x minus 36. Can't combine anything on either side anymore. Does the variable appear just once? Yes. If the variable appeared once on each side, I'd have to take care of that, but it just appears on one side, so we're good. So then we need to add 36. Negative 4x equals negative 32, and then divided by negative 4. X equals, actually a positive 32. 32 divided by negative 4 is negative 8. Right? X equals negative 8. So now I need to come back up here and find y. Doesn't really matter which equation I use, but I have this one right here that I've already solved for y. So y equals 12 plus 2 times negative 8. Twelve plus 2 times negative 8 is negative 16. 12 plus negative 16 is negative 4. So y equals negative 4. So we've got the solution of negative 8, negative 4. What do you think? Let's do one more example. Looking at these here, none of them look real easy to solve. There's none of them that just have a 1x or a 1y. But there's a 2x here and there's a 2y here. We've solved for y so far, but I'm going to argue that solving this one for y isn't going to be the simplest. Can anybody tell me why? Yeah, well, it's a negative. But divide by 2's, these are odd numbers, so it's going to give me decimals. If I solve for x up here, I'm still dividing by 2, but those numbers are even, so it's going to work out nice and neat. So I'm going to solve this top equation for x this time. So to do that, I am going to subtract 4y. 6 equals 14 minus 4y. And then, divide by 2, you got her. 14 divided by 2 is 7. Negative 4y divided by 2 is a negative 2y. Now that I have that, I know that this x, notice I have to go to the other equation. It's equivalent to that x. Robin, you want to grab the test? There you go. Have fun. So you replace this x with the 7 minus 2y. So 3x becomes 3 times 7 minus 2y. We still got minus 2y there, equals 13. So all I did there was I replaced that with that, because it says x equals 7 minus 2y. That'll be nice. So we've got 3 times 7 is 21, 3 times negative 2, negative 6y, and then minus 2y equals 13. Combine the negative 6 and negative 2, negative 8y, and then we still got the 21 equals 13. And then subtract 21. Negative 8y equals negative 8. We'll divide by 8. Divide by negative 8. Y equals 1. Now I need to find x. I'm going to come over here. I'm going to replace y here with 1. So x equals 7 minus 2y becomes x equals 7 minus 2 times 1. 2 times 1, of course, is just 2. 7 minus 2 is 5. X equals 5. So x is 5, y is 1. That's my solution. On page 411, exercise 17.2 deals with this algebraic method of solving them. It is referred to as substitution.